I welcome all of you to the class. In the previous class, we were discussing about the gyroscopic motion, and very quickly I will recapitulate whatever we had done previously. We started with the application and solutions of the Euler equations of motion. First, we derived the Euler equations of motion, and then we tried to apply them on some mechanical systems and find their solutions. Okay, and the rigid body we have under consideration, over which we are understanding these Euler equations of motion, is what we call as the gyroscope. So we are studying gyroscopic motion as an application of Euler equations of motion, and then solving the equations of motion of gyroscope, and its solution comes in two forms. Okay, one is called steady precession solution, and another is called the torque free motion solution, or we simply call it as steady precession and torque free motion, which are the solutions of the Euler equations of motion when applied on the gyroscope. So the term was gyroscope, and these were the Euler equations which we have already derived, and we recapitulated them in the previous class as well. Now, in the previous class, we talked about the motion of a gyroscope and said that the motion of a gyroscope is explained in the form of three angles called the Eulerian angles. As far as the gyroscopic motion is concerned, first of all, we said that a gyroscope is composed of two rings. This is an outer ring. This is called outer gimbal. This is called the outer gimbal, and the inner one is called the this one is called the inner gimbal. Okay, this is called the outer gimbal, and the inner one is called the inner gimbal. Fine, this is outer gimbal. In the same way we talk about the inner gimbal. Fine. Now, apart from outer gimbal and inner gimbal, we have what we call as the disc. Okay, so the disc is over here. This is the disc. Now, in order to understand the motion, we assume that our frame of reference, called the ground frame of reference, has origin at the center of the disk. Okay, and this we treat as our x-axis with respect to the ground, y-axis of the ground, and z-axis of the ground. This is called the reference position. Whatever motion, whenever we have to look into the motion of a gyroscope, we have to assume initially the gyroscope units in this configuration. Now, as far as the motions are concerned, first of all, we talked about the motion of the outer gimbal. As far as the outer gimbal is concerned, the outer gimbal is free to rotate about z axis. Okay, the outer gimbal is free to rotate about this z axis. Fine. So as we give motion to this outer gimbal in this way, as we give motion to the outer gimbal with respect to the z axis, so it certainly rotates by an angle called angle phi. Okay, this is the angle phi. In the same way, as far as the disk is concerned, the rotation of a disk is explained in the form of is expressed in the angle psi. Okay, and the third one is the angle of rotation of this inner gimbal. As far as the inner gimbal is concerned, the inner gimbal is uh, free to rotate, and it is free to rotate about the inner gimbal is free to rotate about y axis. Okay, so as we give motion to the inner gimbal, the motion of the inner gimbal will be in this direction. Okay, will try to give it rotation and try to rotate along y axis. So the angle that is described is called the angle theta. Angle phi, this angle phi, angle psi, and angle theta, these three angles are called the Eulerian angles. Okay, after Eulerian angles, we have what we call as the precession, nutation, and the spin. As far as the precession, nutation, and spin is concerned, precession, nutation, and spin is the derivative of three terms. Now, what the three terms are? First of all, we talked about the angle theta. Okay, the derivative of angle theta, derivative of angle theta with respect to time is what we call as the nutation, as is written here. This is called nutation. The derivative of angle psi, the derivative of angle psi is what we call as precision spin. Sorry, this is called spin. Okay, so as the rate of change of angle of this angular motion, the rate of change of angle of the disk is what we call as the spin. And the third one is what we call as the precession. Precession is the rate of change of angle phi. What is angle phi? Angle phi is the angle of rotation of this. Angle phi is the angle of rotation of the outer gimbal. Okay, this is what we call as angle phi. The derivative of this angle phi is what we call as the precession. So we often talk about that the gyroscope is precessing, the gyroscope is nutating, or the gyroscope is spinning. When we say the gyroscope is spinning, it gives us an indication that the inner disk of the gyroscope is rotating about this, about z-axis. Okay, and when we talk about the gyroscope is nutating, it means that it's rotating about this y-axis. Okay, and when we talk about the gyroscope is precessing, it means that the outer gimbal is rotating about the capital Z axis. Now, before we go ahead and try to understand its equations of motion, we have two important things to keep in mind, as I was discussing in the previous class. In the previous class, I was quite exaggerating over the fact that in order to understand the motion of the gyroscope, we will be using two frames of reference as we have been using previously. The two frames of reference will be our ground frame of reference, and the another frame of reference is the rotating frame of reference. What is our ground frame of reference? As far as the ground frame of reference is concerned, return back to the original position, to the reference position of this gyroscope. Okay, now the frame of reference that you see over here, this capital X, capital Y, and this capital Z, having origin at the center of this disk. Okay, having origin at the center of this disk, this is our ground frame of reference. Okay, so we are assuming that the ground frame of reference for a gyroscope lies at, okay, is in such a way that its center lies at, lies at the at the center of the disk. Okay, that's its origin lies at the center of the disk. This is what we call as the gyroscopic ground frame of reference. I'm repeating, as far as the gyroscope ground frame of reference is concerned, we assume that the ground frame of reference is having this as its x-axis, is having this as its y-axis, and is certainly having this as its z-axis. Okay, and its origin is certainly at the center of this disk. Okay, so this x, this y, and this z is what denotes our frame of reference, what we call as the ground frame of reference. So this is our ground frame of reference. Okay, now we have one more frame of reference, what we call as the rotating frame of reference. In order to visualize it, where the rotating frame of reference lies, let's return back to this figure. Okay, now in this figure, you see we are certainly having three frames of reference again. Okay, so one coordinate axis is this small x, it's like this small x. Another axis is in this direction, in the direction of small y, and another is in this direction, in the direction of small z. This small x, small y, and small z having origin again at the same point at the center of the disk. These three axes represent our moving frame of reference or rotating frame of reference. I will write this as, this is moving or rotating frame of reference. I will write this as moving or rotating FOR, frame of reference. Fine. Now look very carefully. The frame of reference, I am repeating, this moving frame of reference is attached to the inner gimbal. Okay, this moving frame of reference is attached or fixed. I will write fixed, is fixed, is fixed with, is fixed with the inner gimbal. It's fixed with the inner gimbal. What does that mean? This is something important to understand and to keep in mind. Okay, I mean to say is it is fixed with the inner gimbal. I mean to say that the inner frame of reference, that is this rotating frame of reference, this rotating frame of reference is as such. Okay, the rotating frame of reference is such that it's attached with the inner gimbal. Okay, and look at the motion of the inner gimbal. The inner gimbal is having all the motions except, I mean to say is the inner gimbal is attached. Yeah, the moving frame of reference is attached to the inner gimbal. When we say it's attached to the inner gimbal, what does that mean? Look at the motion of the inner gimbal. Okay, the inner gimbal is having nutation. Okay, it's having the angle of nutation, theta. Okay, this inner gimbal rotates with the rotation of the outer gimbal. If you give motion to the outer gimbal, that is, as the outer gimbal starts processing about z-axis, the inner gimbal will also move. But there is one motion that the inner gimbal, that the inner gimbal does not possess. The inner gimbal is having two motions. Be careful about it. Okay, I mean to say that as far as this inner gimbal is concerned, this inner gimbal is free to rotate about y-axis. Okay, that is, it's free to rotate by describing this angle theta. This motion can be observed by, can be expressed by this inner gimbal. Okay, inner gimbal can nutate about the z-axis. Okay, sometimes the angle is theta, theta 1, theta 2. It can have various values of this angle theta. Fine, that is, it can have nutation. And as the gyroscope starts processing, at the gyroscope starts processing, that is, as the outer gimbal rotates about the z-axis, the inner gimbal is also rotating with the with the outer gimbal, because the inner gimbal is attached with the outer gimbal. There is an attachment between the inner gimbal and the outer gimbal. As the outer gimbal is rotating, the inner gimbal will also rotate. Fine. So it means there are two motions that the inner gimbal can have. The inner gimbal can have nutation, the inner gimbal can have precession, but the inner gimbal cannot have the spin. The inner gimbal cannot spin. The reason to it is very simple, because if you look at the inner gimbal, if you look at the spin is associated with the disc. Look at the disc. If you, let me clean the figure first. If you look at the figure, if you look at the spin is associated with the disk. So the disk is spinning. Okay, but as the disk spins about the small z-axis, as the disk is spinning about the small z-axis, there will be the inner gimbal does not spin at all. The inner gimbal does not spin at all. Okay, because the inner gimbal is fixed here. 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 Okay, it will not spin, but only the disk will spin. It means, as far as our frame of reference is concerned, the moving frame of reference is concerned, we have to keep it in mind that our moving frame of reference precesses. It has a precision. It precesses. Our moving frame of reference precesses. Our moving frame of reference nutates. The our moving frame of reference nutates, but our inner frame of reference does not spin. It does not spin. It does not spin. Okay, it does not spin at all. Fine. So these are the two motions. So in the nutshell, we can simply say now that as far as the inner gimbal is concerned, the inner gimbal does precess, the inner gimbal does nutate, but the inner gimbal, sorry, the moving frame of reference does not spin at all. Okay, the inner gimbal or this motion. Now let's write the equations of motion. What equations of motion we can have for the gyroscope? As far as the gyroscope is concerned, the motion of the gyroscope is concerned, in the motion of the gyroscope, the first and foremost equation that I will write is the angular velocity of this gyroscope with respect to an observer on the ground, with respect to the ground frame of reference. Let's suppose an observer on the ground is observing the motion of the gyroscope. Okay, and the gyroscope at this time is in this configuration. It is processing, it is nutating, as well as it is spinning. So the observer on the ground will say that the angular velocity with respect to the ground is equal to angular velocity with respect to the ground is, first of all, he will talk about, he will say that this gyroscope is rotating about z, capital Z axis. Okay, it's rotating about capital Z axis with an angle, and we know the overall rotation of the gyroscope along Z axis is with an angular velocity that's called the precession. We represent that by phi dot. It will say that its angular velocity along Z axis, it's precessing along Z axis, that is phi dot, but along capital K axis. Okay, this will be the first. An observer on the ground will say that the gyroscope is precessing. Okay, that is, the outer gimbal of the gyroscope is rotating about this capital Z axis with an angular velocity given by phi dot, known as precession. Number one. Number two, he will also say that the gyroscope is nutating as well. Okay, that is plus, I will write it plus. It's also having angular velocity. Okay, it's precessing, it's going back and forth. Okay, it's rotating about this y-axis with an angular velocity given by theta dot. Okay, and when you look at this angle description, when you see this angle description here, as it's rotating about this small y-axis, the rotation is along this y-axis, and the unit vector along y-axis we define as j cap. So it is small j cap. Okay, and the third motion this gyroscope will have will be the spin. The observer on the ground will say that the gyroscope is also spinning. Okay, the disc of the gyroscope is spinning, and if you curl your fingers in this direction, the thumb will be along the z-axis. And we know, as far as a spin is concerned, it is defined by psi dot. So it is psi dot. The gyroscope is spinning psi dot along small z-axis, that is small k cap. This is the motion of this gyroscope. Now look, as far as the angular velocity of the gyroscope is concerned, it is being expressed in terms of nutation, precession, and spin. But j cap is a unit vector along small y-axis. K cap is a unit vector along small z-axis. But look at this k cap, this k. As far as this capital K is concerned, it represents a unit vector along capital Z axis, which is a ground frame of reference axis. Okay, so now a unit vector drawn in this direction can be resolved. If we have a unit vector in this direction, that is, if we have a unit vector K in this direction, it can be resolved into two components. One component will be in this direction, and another component will be in this direction. Okay, and this angle here is angle theta. We can say this is unit vector along, this is capital K, this is a unit vector along capital Z axis. Its component along this direction will be, this component will be K cos theta. Since K is 1, that will be cos theta small k cap. And this component will be minus sine theta. Since this is K sine theta, K is 1, therefore it will be only minus K sine theta. It's actually minus K sine theta, okay? But K is equal to 1, therefore it's minus sine theta along I cap. Okay, why this is minus? Because it's along negative x-axis. Therefore, substituting the values of this k components in this equation, we will get angular velocity with respect to the ground is equal to, we can write this as, this can be written now as, this is equal, can write this as phi dot, and in place of k, we'll write it has two components. It has cos theta k cap, cos of theta small k cap, minus sine of theta I cap, minus sine of theta I cap. This is our k. Plus we have theta dot along small j cap, plus phi dot small k cap. Okay. This can further be modified as, we can modify it as and write it as omega is equal to, we can write this as, let me write it over here. We can write this as angular velocity. Okay, let me okay, fine, let's write it here, angular velocity. Let me not subscript it by j, because I know it's with respect to ground. This can be written as minus phi dot, this can be written as minus phi dot sine theta, minus phi dot sine theta I cap. Okay, then j component plus theta dot j cap. This is the second component. And the third component will be, we have plus, I'll write this as plus. Okay, we have the third component will be psi dot, this is psi dot plus phi dot cos theta, plus phi dot cos theta, phi dot cos theta, and it will be along k cap. Let me drop it over here. It will be along k cap. Okay, let me write the small k cap. This is the expression for the angular velocity. Okay, so this is the angular velocity of what? This is the angular velocity of this total gyroscope with respect to the ground. Now we know, as far as look into the axis again, as far as the axis that we have selected are concerned, okay, as far as this capital X, capital Y, and capital Z are concerned, if we return back, okay, so after writing this expression, we know the capital X, capital Y, and capital Z, they are selected in such a way that capital X was passing like this, capital Y was also transverse, and capital Z was along the capital Z axis. Okay, I mean to say, let me okay, I hope that you have copied this expression, because I need to return back to just make you Yes, over here. If you look at the capital X, capital Y, and capital Z, the x-axis and y-axis, you see here, our x-axis is like this, okay? Our y-axis is like this. And if you look at this x-axis and y-axis, capital X and capital Y-axis, they are also the axis of symmetry, okay? And we know from they are the axis of symmetry because they divide your overall system into two symmetrical portions, okay? They are the axis of symmetry. Now we know as far as the axes of symmetry are concerned, axis of symmetry happens to be what we call as the principal axis. Okay, the axis of symmetry happens to be the axis over which the product of inertia is equal to zero. We know it. Okay, the axis of symmetries are the symmetries over which the product of inertia is zero. Okay, now let's assume the product. Let's assume the moment of inertia about this x-axis by as I. Okay, and also assume the moment of inertia about y-axis. Okay, uh, the moment of inertia about z-axis. Let's assume the moment of inertia about z-axis as I. And since this x-axis and y-axis, okay, for this disk they are same, we assume the moment of inertia about them I prime, and moment of inertia of the disk about this also as I prime, because both these axes are transverse and same axis. Whatever is the moment of inertia of the disk about x-axis, the same will be the moment of inertia of the disk about this y-axis. Okay, so what we say, the moment of inertia about the z-axis is I, and the moment of inertia of this disk about x-axis and y-axis is I prime and I prime. Okay, now we return back to our diagram that is over here. Now as far as the if we are asked to calculate the moment of if we are calculate the angular momentum of the disk, angular momentum of the disk about point O is equal to I multiplied by omega. This is the general expression for it. Okay, now we know as far as omega is concerned, we already have we have just derived the expression for omega. And as far as the moment of inertia is concerned, we also know the moment of inertia about x-axis, y-axis, and z-axis. Therefore we can write the angular momentum of the disk. We can write then the angular momentum of the disk, the angular momentum of the disk about point O is equal to, we have omega. Let me first repeat the expression for omega, so that the expression for omega is, which I have just claimed, is equal to minus phi dot minus phi dot minus phi dot sine theta I cap, sine theta I cap, plus theta dot j cap, plus theta dot j cap, plus phi dot plus psi dot plus phi dot plus phi dot cos theta k cap, small k cap, cos theta small k cap. This is our angular velocity. Now if we multiply this angular velocity with the corresponding moments of inertia, then we will get the angular momentum. Therefore angular momentum will be, so this is angular velocity along x-axis. We have to multiply it with the corresponding moment of inertia, and the moment of inertia along x-axis we are seeing is I prime. So it is I prime, so it will be minus I prime uh, phi dot minus I prime phi dot sine theta I cap, sine of theta I cap. This term gives us the angular momentum about x-axis. Okay, so you have to multiply angular velocity with the corresponding moment of inertia term, plus we have theta dot along j cap. As far as j cap is concerned, the moment of inertia along j cap is also I prime. Okay, they are in the same value, so it will be I prime theta dot j cap, I prime theta dot j cap, plus the moment of inertia about the z axis we are assuming to be I, so it is I psi dot plus theta dot cos of theta, fine, along k cap. So these terms, by multiplying the angular velocity term by the corresponding moments of inertia, we are getting the values of the angular velocity. Okay, now Now I will call this as angular velocity equation as equation 1. This equation let's call as equation 2. And the third one that's very important for us is what we call as the term of the motion of the motion of the rotating frame of reference. Okay, as far as the rotating frame of reference is concerned, the angular velocity of this rotating frame of reference is concerned, I will write this as angle WRT subscript angular velocity of the rotating frame of reference with respect to the ground frame of reference. Certainly angular velocity of the rotating frame of reference with respect to the ground frame of reference will be equal. What it will be equal, by the way, the angular velocity of the rotating frame of reference with respect to the ground frame of reference will be equal to what? Now observer is on the ground and he's observing the motion of this rotating frame of reference, which we are expressing by small x, small y, and small z. What he will say? He will say that the inner frame of reference or the rotating frame of reference is rotating about the z axis, that is, it's having precession, it's having nutation, but the inner frame of reference or this rotating frame of reference is not spinning at all. Okay, because our frame of reference, the inner frame of reference, is attached to what? It's fixed with the inner gimbal. Okay, but the inner gimbal is not rotating at all. It is the disk which is rotating. The inner gimbal is not rotating. So it means the rotating frame of reference with respect to the observer is having precession frame of precession motion. It's having nutation motion, but it does not have spin at all. That is, the observer on the ground will say that the inner frame of reference motions are, it is precessing, that is, its motion is phi dot about capital K axis, and it's also nutating, that is theta dot along y cap, that is theta dot j cap. Okay, that means that's equal to, along we know the values of uh, this k cap. So as we substitute the value of k, we'll get it is phi dot, and the value of k in terms of its components, we can write this as sine theta I cap, as we have written here. Okay, sine theta I cap, but minus sine theta I cap plus our this theta dot j cap. We'll write this as plus theta dot j cap, theta dot j cap, and the third component is plus phi dot cos theta k cap, phi dot cos theta small k cap. The reason is because we know, as far as the capital K is concerned, the components of capital K are uh, components are cos of theta along small k cap minus sine of theta along I cap. Okay, this is the unit vector along k. Substitute the value of k in this equation, we'll get this value. So this is the angular velocity of the rotating angular velocity of the disk with respect to the ground frame of reference. Now, once we have two expressions, once we have this expression and the next expression, with the help of these two expressions, we can find out the moments that we'll be doing in the next class.